Hello, this is something I just worked on the bench today because I came across a circuit which basically lets you create, it basically works as a super capacitor protection board essentially. And I've replicated something similar using different components. So the small chip on the breakout board there, I believe that's it's a soft. It's a SO8 pin package, right? It's this one. It's this Max 61. Actually, the one I'm using is the 10 volt version, so it's this Max 61. Hold on, let me just flip through this. 6173. Yeah, 6176. It's this one down here. And the way I wired it up is essentially in this same config, identical to this. I left out the capacitor on the side, just basically supplying for 10 volts output. You basically supply V out plus 2, so it's 12 volts, and you have a trim part on the outside, on the output at least, yeah. And you get reference output. I even tested the temperature output, which is pretty neat. It gives you a temperature reading in millivolts, but I won't be doing temperature testing on this right now, but later I might play with that. So we've got the 10 volts output, and then I've wired up a pot here. The legs are too short to go into the breadboard, so I've used this little proto board, right? So I used that, and up here I basically trimmed or tuned the pot at least to get a stable 10 volts reference. I didn't want to. We didn't want to push it any further, but this is stable enough for this test, right? And then what happens next is, let me show the Opamp. So that's an Opamp. It's a very simple Opamp. It's the LM324N. It's one of these, right? So the LM324N is the one I'm using. I'm looking at the dip package. So I'm basically using this single number one. Ideally, you would tie 2, 3, 4 into the unused configuration. If you Google for Texas Instruments, it gives you basically a schematic of how it should be wired onto the PCB at least, right? So here it's just basically got the inverting input pin number 2 and the non-inverting input number 3, and the output is pin number 1. So that's basically over here, right? And what I first did was I basically tested providing the 10 volts reference onto the non-inverting input. That's taking the 10 volt reference from here and providing that there. Let's see which pin is that. Oh, so that's the orange wire. So this orange lead going across, that's to the non-inverting input. Okay. Now hang on, let me just catch my train of thought here. Oh yes, and then I basically onto the on the inverting input. The inverting input has the 10 volts reference, and then onto the non-inverting input I provided 10 volts from my power supply. So that's a handy thing to have multiple outputs. So on the third channel I provided 10 volts, and you can see it's 10.036. That's because I was twiddling with the knob. And so basically when the non-inverting input is higher than the inverting input, the output raises up to VCC. In this case, VCC to the Opamp power is 12 volts as well, right? And then if it goes below, it goes down to 0 because this is wired in the single rail configuration. Okay, that's also important. And then that proves that the op-amp is working as a comparator. Essentially, it's comparing its inputs, and the output becomes essentially a pulse, essentially, depending on the state of the inputs. So the reference now in this case is a 10 volts reference, a stable 10 volt reference. That's why that's important. Okay, let's start this back again. And you'll be wondering, okay, why do we have 10 volts up here? And we'll come back to that. And what I did next was to essentially, one second, pull up this schematic in here. Okay. Just trying to sort out my papers on the side here. Here we go. Here we go. It just made this very rough schematic. So the cap is connected to the rail. We have a 10 voltage ref. Then the output from the op-amp drives a MOSFET. We have a 1 kilo ohm connected to the drain. The output of the op-amp drives the gate, and source connects to ground. So essentially what we're saying here is, if the capacitor voltage is driven higher than 10 volts, I want to bleed off that excess voltage off the capacitor, right? So let me show you something here. If I pull out the source pin, this is the source wire, right? Look at the capacitor voltage. It's going to go to the rail voltage, essentially. And you can see that this is essentially the output of the op-amp, right? This is the output is giving. It's got a, let me show you the supply voltage. It's actually being provided 12 volts, 11.99. But this is its rail output. And so as soon as I connect, oops, let's not get this wrong way around. As soon as I connect this back in, it bleeds out the rest via the MOSFET. Take it off again. It's fully saturated there. Now, thankfully for this circuit, right, this little chip over here can handle up to 40 volts input. The LM324N has a real, it supports up to, let me check the documents again. Here we go, lovely. Single supply 3 volts at 30 volt 2 volts, right? And the MOSFET here, it's well over spec MOSFET. It supports a gate voltage of up to 20 volts. So that means we could essentially push this voltage here from 12 to 20. Now, if we were to do that, let me just actually take this pin off. Let's look at the capacitor voltage. This is a 35 volt capacitor, 1000 microfarad, right? So we're safe on that as well. So let's go here and punch in 20. And our capacitor voltage rises up to, almost 20, 19.5, and this is the output of the op-amp in its current state, essentially. So the op-amp right now is actually getting the signal from the voltage of the cap. So it's seeing that, but I just haven't tied the MOSFET to ground, right? So as soon as I tie MOSFET to ground, the cap voltage drops. Let me just take it off again. It'll drop from that value to. So if we were to tie a DMM to check the voltage against drain and source, right now it's bleeding off about 10 volts. And how do I know this? It gets warm. It really starts to get warm, because now it's pulling about 100 milliamps, and it's getting warm. So I'm just going to back this down again to 12. I don't want to overheat it. It's a pretty good MOSFET, and still stays at 10. And the reference is at 10. And of course I just used a scope earlier to watch the output toggling. So it was just handy. I didn't do too much with the scope beyond that. And this is now, once it's connected in this configuration, it's compensating. Interestingly enough, this is the output that the Opamp is providing, and that locks the voltage on the capacitor to 10 volts. And if I were to actually toggle the let's do it, why not, because I'm on the video, right? If I were to retrim the input reference, right, I were to retrim it to say 10 point this thing. Oh, let's drop it. You can see how the capacitor voltage is affected by it, and that's the whole point here, right? I'm basically controlling the max capacitor voltage by this external reference voltage, and that's great. So which means if this circuit was tied to this capacitor, whatever the external voltage applied, it's going to basically protect the capacitor and prevent overcharging it. And that's the other point. If you have the cap attached to any voltage with any low current even, it's always charging, right? So with this you can prevent the cap charging beyond a certain voltage, and that's important because you can have 2.5 volts, 2.7 volt super caps, and you don't want to let them overcharge, which essentially destroy them. And so this little circuit works great. Works far better than I expected. I hope you found this interesting. Thanks for watching. Bye.